The smooth, rounded stone in this casket is one of the world's most precious gems. Though it has no glitter, no flash or fire, it commands the respect and admiration always accorded the finest thing of its kind. For this is the Star of India, the finest star sapphire in the world. Turn it this way or that, the perfect six-pointed star gleams soft and bright. This is a ship's chronometer. In its own way, it is in the same class as the Star of India, for it too is the finest of its kind. So perfectly is it constructed, so accurately and precisely does it perform, that ships of every kind rely upon it to determine their position at sea, which they must often count on as being correct within a matter of not miles, but yards. To a large extent, this superlative degree of accuracy resides in the bearings on which the pivots of the instrument turn. These bearings are made of red sapphire, commonly called ruby, which is one of the hardest known substances in the world. It is hard enough so that many years of constant running will leave no mark upon its surface or measurably wear it away. This is a star ruby, and is one form in which the natural gem is found. Ruby and sapphire are chemically alike. Sapphire may be pure white, like this stone, or may be any one of many colors, including red. These gems are museum pieces, whose beauty and nearly flawless purity are reason enough for their preservation under guard. The ruby of the jewel bearing is many times as pure, and is really flawless, although it is made in furnaces from humble material. The jewels of a chronometer are comparatively large, perhaps 50 times the size of those made for a tiny wristwatch. So, for these pictures, we have chosen to photograph the large chronometer jewels in order to make the operations as clear and understandable as possible. This is a piece of synthetic sapphire just as it came from the furnace. It is called a boule. If you tried to cut or saw it, it would shatter into useless fragments like these because of the internal stresses created during manufacture. But it can be split cleanly with a hammer blow at the right point. The resulting halves are free of stress and can be cut up for jewels with comparatively little fear of damage. Both white and red sapphire or ruby are used in jewel making. They are alike in composition, except for a small amount of chromium oxide which gives the ruby its color. This diagram shows the successive divisions by which a boule is reduced into jewel blanks. The first step is to split the boule along its natural line of cleavage. This produces the half boule, which is the form in which the gem is delivered for processing into bearings. The half boule is sawed into thin sections, much as a loaf of bread would be sliced. Each one of these sections is called a half moon. Each half moon is in turn sliced into narrow strips, and these in their turn are cut into little squares. The squares have their corners rounded off and are then ground into circular flat blanks, which are known as preparage. And that's how a boule is cut down to the little blanks, which are the real starting point in making bearing jewels. Up to 95% of the original sapphire will have to be sawed or ground away to produce the finished jewels. All this sawing and grinding is done with powdered diamond, because diamond is the only substance hard enough to cut sapphire economically. So the real starting point in jewel making is the preparation of the diamond powder, our most important working tool. We start with rough pebbles of commercial diamond called bort. A few of these pebbles are dumped in a hard steel mortar, then a special alloy pestle is put in place and struck 3 blows with a hammer. The resulting mixture of diamond particles is dumped into a hand sifter, and another handful of pebbles goes into the mortar. The 3 3 hammer blows reduce the pebbles to a mixture of particles varying in size from extremely fine to very coarse. When a batch has been accumulated, the hand sifter is used to separate out the crystals which are too coarse. These will be further hammered. The remaining mixture of finer particles which pass through the sifter is then put into the top sieve of the shaker. This is a stack of graduated sieves mounted on a motor-driven shaker. The screens, which get finer toward the bottom of the stack, will separate the mixture into a series of grades of powder suitable for the faster, rougher cutting and grinding operations. Automatic hammers are used to obtain finer grades of powder. The diamond, which passes the finest shaker screen, is pounded in this machine for a period of about a half hour, reducing it to very fine particles. These finer grades of powder cannot be sorted by sifting, but are separated by gravity grading or levigation. In this process, we start with a powder which contains a mixture of all finer particle sizes. A small quantity of the dry mixture is measured out into each one of these porcelain dishes. After olive oil is added, the contents of each dish are stirred in the traditional way. Then they are allowed to stand and settle for a measured length of time, during which all particles over a certain size will settle to the bottom, leaving all the finer ones still in suspension. Then the fluid is poured off into another set of dishes. The large particles stay behind. The others go into the fresh dishes and begin the next settling period, which is just enough longer than the first to allow the next smaller sized particles to settle. This process is repeated once for each grade desired, according to a precise timetable that allows only 10 minutes for the first settling period, but takes 5 weeks to complete the whole cycle for one lot. The successive pourings always proceed upward in the cabinet. This reduces the possibility of stray particles of larger sizes contaminating the finer powders. Every other step in the preparation of diamond powder is likewise calculated to protect the purity of the finished powders, for one coarse particle in a batch of fine powder can ruin many jewels. In fact, the success or failure of the whole jewel plant depends upon the purity of its diamond powders. For some grinding and polishing jobs, a powder has a less harsh action than ordinary diamond powder. This rolling machine is designed to produce such a powder, which is said to be dulled. The powder to be rolled is first blended with olive oil, usually being allowed to stand overnight before rolling it. The mixture is spread over the whole surface of the larger roll, distributing it uniformly. The dulling effect is secured partly by milling the powder with oil, so as to get a very intimate mixture, with every particle wetted by the oil, and partly by breaking down the diamond. The steel rolls are as hard and as smooth as they can be made, and the pressure is heavy. Rolling times vary from 1 to 80 minutes. The finished mixture has only to be scraped off the rolls and put into a dish for delivery. Most grinding is done with laps. The lap is the large cylinder. It is made of forged copper, charged with diamond powder, and operates by turning against the jewels. This is how such a lap is prepared. The surface of the copper cylinder is cut full of fine grooves, closely spaced. This is done by threading it in a lathe. Diamond powder, a small quantity at a time, is mixed into a paste with carbon tetrachloride and a very small amount of oil. Then it is carefully packed into the grooves of the lap. During this operation, the utmost care must be used to avoid waste of the precious diamond, and at the same time, get every groove uniformly packed full. The next job is to get the particles firmly embedded in the copper, which is merely the holder or carrier of the hard, sharp cutting particles. This is done in a charging machine. The lap goes between a pair of power-driven rolls made of very hard steel. The big hand wheel is used to bring the steel rolls against the lap and apply pressure to it. Oil keeps the copper and diamond from sticking to the steel rolls, and the spatula redistributes the diamond that gets squeezed out, until finally all of it is forced into the surface of the lap. The trick of making a good lap is to use very high pressure on the rolls and reduce the rolling time as much as possible. This technique results in a minimum of crushing of the diamond particles and makes a more durable lap. The same general method is used in preparing saws, which are made of circular bronze blanks, the edges of which are charged with diamond powder. First, the blanks are stacked on an arbor. This will make a solid cylinder of the batch of saws so that all of them can be conveniently treated at once. In order to make the copper blanks hold a maximum quantity of diamond powder, the surface of the assembled stack is cut full of slots in a milling machine. These slots will be packed with diamond, just as the grooves in the lap were, and rolled into a solid mass in the same charging machine. Then the stack can be taken apart and the individual saws washed clean of oil. Next, the saws are clamped, one at a time, to a face plate, so the edges can be rolled flat and true with a hand rolling tool. These saws are usually assembled in gangs, which are used to make a number of parallel cuts at one time. The plastic washers, colored to indicate thickness, are combined in groups to get the required distance between saw blades. The mechanic, nevertheless, checks each group with his micrometer before assembling it in the stack. Plastic washers are used to keep down the weight of the assembly, important because of the high speed at which saws are run. The blades must be handled with great care to keep them flat and true, otherwise they will chip the sapphire and make a ragged cut. When the whole gang is complete, the last operation is to make certain of correct spacing by using a sapphire thickness gauge to check the distance between saws. The first manufacturing operation is to mount or block the boules for sawing into half moons. This is done by cementing them flat side down to hardwood blocks with sealing wax, using an electric stove to keep wax and boules at working temperature. The slicing of the boules into half moons is done on an automatic boule saw. This machine has 4 cutting heads which operate simultaneously. It has just finished a complete cycle, and the operator is lifting the saws out of the way so he can remove the sawed boules and replace them with a fresh lot. This close-up shows how the boule is sliced up. Each half moon is still held in place by the wax, although the saws have cut through the sapphire and into the wood. Now, the next lot of boules is clamped to the table of the machine. Each one is placed under its own saw, then the heads are lowered to their starting position, which is still above the boules and clear of them. The weight of the heavy cutting heads is borne not by the saws resting on the boules, but by a set of slowly moving cams. These cams lower each saw gently into the surface of the boule and control the speed of its progress. A very liberal stream of coolant is essential to keep the blades cutting free and cool. The rate of descent is slow enough to allow the saw to cut freely without binding or undue pressure on the edge of the bronze. When the cut is complete, the cams raise the saws clear, and the table of the machine automatically moves into position for the next cut. This is a planer. It is used for grinding irregular half-moons and boule ends down to uniform thickness. The pieces are shellacked on the block, which is clamped on the planer table. A cylindrical lap to do the cutting is mounted under the gray cover. As the machine runs, it gives the block a side-to-side motion that helps the lap cut true and even. As fast as the lap grinds the pieces down to thickness, the planer table is pulled forward by a cord and weight arrangement. When the whole block is finished, the weight pulls it clear of the head and the machine can be stopped. This girl is getting ready to mount half-moons on blocks so they can be sawed into squares. After covering the blocks with powdered shellac, she puts them on a hot plate so the shellac will melt into an even coat, which will later be allowed to cool and harden. In the meantime, she takes this glass plate with lines ruled on it and mounts it in a lantern slide projector located over the bench so it will make an image of the lines on the workspace below. All this has been figured so that the lines on the bench correspond exactly to where the saw cuts will come when the half-moons are later sawed into squares. Guided by these projected lines, the operator can locate each half-moon so it will yield the maximum possible number of whole squares. In the meantime, the half-moons have been kept on the hot plate so they are able to melt their way into the shellac, which is now cold. Using the projected squares as guides, it is possible to get 5 or 6 large squares out of a half-moon that might only yield 2 or 3 if it were placed at random. The sawing of the squares is done on a gang saw. This is the saw gang made up with the correct spacers between saws to produce the required size of squares. It is mounted on the spindle and made fast. When the cover is in place, the machine is ready and we can proceed to saw up a block of half-moons. After the block is clamped on the table, the machine is started and the block begins its slow journey into the saw blades. At the far end of the machine, the block is now emerging from under the saws. Although you can't see them, the half-moons have now been cut into strips. The operator releases the fixture which holds the block, rotates it through 90 degrees, then starts the machine in reverse. At the end of this pass, the block comes out at its original starting point, the half-moon strips having now been cut into squares. At this point, the square blanks may vary considerably in thickness. In order to make economical use of them, they must be sorted into groups or families. One way of doing this is with a sifter. The main body of the sifter is like 2 pie tins, clamped together by a central nut. The removable spokes are really spacers, which hold the edges of the two halves apart by a known distance, depending on the thickness of the jewel we want to sort out from the others. The jewel blanks are, of course, in the center inside the two pie tins. When the whole business is tipped on edge, those blanks that are thin enough will fall out through the spaces between the two halves. When no more will fall out, the operator can increase the spacing of the halves and sort out the next larger size. The squares of a sifted group still vary a little in thickness and contain some wedge-shaped pieces, so the next step is flat grinding. This girl is mounting the squares on blocks preparatory to grinding. A block is prepared by first heating it on a stove, then applying shellac to the surface, then a layer of paper, and finally a coat of shellac on top of the paper. After this, the block is set aside so the shellac will cool and harden. The prepared block is now ready for a load of jewel blanks. Working under a large magnifying glass, the operator dumps the squares onto the block, then distributes them evenly over the surface, mainly by shaking. Finally, she uses a little spatula to push the blanks about until the block is fully covered. Then off comes the loading ring, and onto the stove goes the block. The shellac will melt again and cement the jewels to the paper. Adding some sheets of cellophane and a little talcum to prevent sticking, she puts the block under a pneumatic press, which holds the jewels down tightly until the shellac hardens. This is a rotary surface grinder. It is a high-precision machine for flat grinding and can handle as many as 40,000 jewel blanks at once without batting an eyelash. These blocks are the ones we just saw loaded. They are held in place in the grinder by a circular magnetic chuck. The mechanic makes sure the bottom of each block is free of dust or dirt particles and seats each one firmly on the surface of the chuck. When the chuck is full and the magnet turned on, he cranks the chuck carriage into its running position, which brings it partially under the resinoid bonded diamond lap. When the machine is running, each block of jewels is thus fully exposed to the action of the wheel. Although the speed and depth of cut are under precise electrical control, the operator of this machine has a very exacting job, for one false move could spoil 40,000 jewels. This is how the jewels, after being ground on one side, are turned over for grinding on the second side. Having once more melted the shellac that held the jewels, they can be scooped up from the block, paper, jewels, and all, just like a flapjack. The next move is to recoat the block, which is still hot, with shellac. Then pick up the paper of jewels and lay them finished side down on the new coat of hot shellac. No paper between block and jewels this time. Just as before, a couple of layers of cellophane and some talcum to prevent sticking, then into the press to cool under pressure. Hand grinding is often used when the quantity of jewels is small. The grinder consists merely of a copper lap mounted on a small bench lathe. A small sponge, frequently dipped in water, is used to keep the lap wet. The jewels are mounted on a small block, but otherwise are handled the same as the large blocks for rotary surface grinding. Frequent checking with a thickness gauge is required to ensure that the jewels are not ground below size. After flat grinding, the corners of the squares are still sharp. The next step is to tumble them, which will round off the corners and leave the blanks looking like this. The tumbling barrel is a round container lined with a special abrasive wheel and partly filled with water. Into it go the jewels. Then water and jewels are sealed in with a gasket and cover. When the barrel is later put in motion, the jewel squares will tumble against each other and the abrasive lining. This will wear the corners off to a rounded shape. The water is to cushion the impact of the jewels against the abrasive and each other, thus preventing excessive chipping. When the cover is tight, the barrel is fastened to one end of the arm in the tumbling machine. A similar barrel is already in place on the other end. The barrels must be tightly fastened on the arm, lest they fly off when the machine is running. The safety cover must be closed before the machine can be started. This girl is getting the tumbled squares ready for rough grinding. When she has finished filling the little trough, the next move is to fold the end of a strip of paper for easy handling, then coat one edge of it with ordinary bees' honey, used because it will dissolve away in the cooling water of the grinder. Now she slips the paper under the row of squares, snugs the jewels tightly together, and the loaded strip is ready for the grinder. There's a special trick to this job, and here it is. The jewels to be loaded are put in a small metal cup, then from 3 to 5 drops of olive oil are added. Then the cup is shaken until the squares adhere to each other in clusters or chains. A squirt of benzene in the trough will keep the jewels from sticking. The fact that the jewels are in little chains makes it possible to stack them in the trough easily and quickly. In the rough centerless grinder, the jewels rest between a cylindrical copper lap and a rubber regulating roller. The cover carries a steel blade which rests on the jewels. After the paper loading strip is pulled out, the stop can be set against the end jewel, and the machine is ready to start. The diamond-charged lap, now hidden behind the jewels and the steel blade, turns against the jewels and does the grinding. The jewels are kept turning by the rubber roller in the foreground, which is independently driven at a speed found by experience to produce the best results. As the jewels grow smaller and smaller, they let the steel blade and the cover down lower and lower. At a predetermined point, a projection on the cover trips a sensitive switch, which stops the motor. Then the operator lifts the cover, turns the lap backwards a little to free the jewels, and picks out a sample to test for size in the gauge. Its diameter was within specified limits, so she takes another from the other end of the load, just to make sure the grinding was even. Well, we finally got our boule cut down to something that begins to look like jewels. But there's still a long way to go. These blanks aren't even very round as yet, much less down to a standard size. But both these shortcomings will be corrected by the medium centerless grinder. This operation is similar to rough grinding, except that it is much more accurate and results in a more nearly perfect circle. It is done on a similar type of machine. But this time, the steel blade is underneath, and the jewels are supported by its upper edge, on which they rest during grinding. Since they are round to start with, they do not punish the surface of the lap as severely as the square ones. On this machine, the steel blade remains stationary, but the rubber roller comes nearer and nearer to the lap as the jewels are ground smaller and smaller. When it gets near enough to indicate that the jewels are down to size, it trips the automatic cutoff switch and the machine stops. Test jewels are taken this time from 3 points in the row to make certain of uniform grinding, and the diameter is held to much closer limits than before. Medium grinding gives us blanks like this, known as preparage. This is the starting point for the sequence of finishing operations that will produce the completed jewel. This is the spotting machine. It produces a depression or spot in the center of the jewel, which will serve as a guide for the drill point. On each of the 3 heads, a cam controls the motion of the tool, putting the pressure on just long enough to get a good spot, then retracting the tool and opening the chuck. So all the operator has to do is to place the jewel in the chuck and press the start lever. After the control cam has completed its cycle, the tool rises and the chuck opens. Then the operator removes the spotted blank and starts another on its way. This is what the spotted blanks look like. This machine has an additional feature used when spotting small jewels. The rear pipe is connected to a vacuum line. It automatically swings over the chuck and picks up the spotted jewel. This enormously speeds up the job, since the operator has only to load the chucks. This is the machine that does the drilling. It has 24 drills working on 24 jewels at once. Each jewel is held in a small removable chuck. As soon as the operator sees that one is drilled, she removes the chuck, releases the jewel into a cup of benzene, picks up a fresh one, and applies to it a mixture of petrolatum and diamond powder, using the least powder that will cover the spot. Each drill consists merely of a bit of fine steel wire. Spinning at 28,000 RPM, it grinds the diamond powder into the jewel to produce the hole. Frequently, the drills break or wear out and must be replaced. Each drill is held in its chuck with shellac. A spirit lamp melts the shellac so the old drill can be pulled out. The fresh drill is heated in the lamp flame, then inserted in the chuck. Now fresh shellac is added by holding a stick of it against the heated chuck. Then the lamp is taken away. While the shellac is cooling and setting, the operator uses the tweezer points to spin the new drill true, meanwhile relaxing her hold on the back end of the spindle, thus allowing it to turn faster and faster. When the drill is finally running true, she can let go the spindle, set a new jewel in place for drilling, and the routine continues as before. Drilling sometimes causes invisible surface cracks. Also, some wedge-shaped blanks may have escaped detection up until now. These defects are remedied by a second flat grinding operation after drilling. Then the jewels are ready for opening, which brings the holes to final size and finish. Opening is done in 2 stages, rough and final. This is the rough opening machine. It has 2 identical spindles and can run 2 loads at once. The jewels can be seen in the rotating cage or spinner, which turns them, while a diamond-charged wire is drawn back and forth through the holes. The diamond gradually cuts the hole larger until finally it has reached the limit for that size of wire. Now the wire is made so that each 5 feet along its length, it changes to a slightly larger size. After the machine runs for a time on one wire size, or step, the charged wire will enlarge the holes in the jewels enough to admit the next larger step. Then the operator stops the machine, loosens the spools, and pulls the tapered step wire through the jewels until the wire gets too big to enter the hole. At this point, it will, of course, stick, since the holes in the jewels are not yet large enough to allow the next step to enter. Then the wire must be reversed or backed up until the step which will not enter the jewels is safely out of the way on the feed spool and cannot jam into the jewels when the carriage is started. Then the wire is pulled tight and clamped at the take-up spool, and the machine is started for the next run. A little diamond is applied to the wire at the points where it enters the spinner at the beginning of each 3-minute run. It takes about 3 minutes of running on each size of the wire to work the holes out large enough to admit the next larger step. This process is repeated until the last step of the wire is in the jewel. For the final run, only about a half turn of wire is left on the feed spool. Again, it is drawn tight and clamped, the machine is started, and diamond is applied. On the last step, the machine is allowed to run 5 minutes to make certain that the holes are as large as the wire will make them. Now comes the time to unload the machine. The spools are loosened and the wire is wound back onto the feed spool, pulling its entire length through the string, except just enough to hold the jewels. Then the plug which held them in the spinner is removed, and finally, the jewels are fished out through the plug opening, being careful not to lose the end of the wire. All there is left to do is to push the jewels off the end of the wire into the pan in which they will be sent to the cleaning department. Loading the machine for the next run is just a reversal of the unloading process. The jewels come loaded on the small end of the step wire. After pushing them back to get room to work, the free end of the wire is threaded through each end of the spinner in turn. Then it is taken to the take-up spool and secured there. Then the string of jewels is carefully pulled into the spinner, and the plug, which was also threaded onto the step wire, is inserted in its opening. Then the right spool is clamped, the wire is pulled tight onto the left spool, and it is clamped. Now the plug is pushed all the way home, clamping the string of jewels endwise, then backed off a distance about equal to the thickness of one jewel and tightened in that position. The step wire is wound onto the take-up spool as far as it will go, then reversed onto the feed spool to get the next step safely out of the way, just exactly the way we did it before. And the machine is set running. The usual touch of diamond is applied to the wire to give it its cutting edge, and another batch of jewels is on its way. In the final opening of holes, the same identical principle is used as in the rough opening, and the work is done on the same type of machine. But now the jewels are held rigidly in wax to ensure accurate hole alignment. A finer grade of diamond powder is used, and they are spun rapidly to ensure the holes being truly round and to give them a high polish. The technique of loading is a little different. Jewels are delivered strung on a short loading wire, used merely to set up the machine and make the initial run. The two ends are passed through the ends of the spinner, each from the inside out, and fastened to the spool. After the string of jewels is in place in the spinner, the plugs are set tightly against the ends of the string and centered up so that both plugs project into the spinner the same distance. It is important that the wire is carefully lined up, drawn tight, and in place in its guide wheels at this time. Then a plate is coated with olive oil and blocked under the spinner, taking care not to get it tight enough to bend the bars of the spinner. Then the wax is poured around the jewels, carefully filling all the space. Pulling the carriage back and forth will prevent the wire from freezing in place due to expansion from the heat of the molten wax. After the wax is hardened, it is necessary to wave or crimp the loading wire before starting the machine. This is to make sure that the wire really exerts pressure against the inside of the hole, so that the fine diamond powder can do its work of cutting the jewels. After a little diamond is put on the wire, the carriage and spinners are worked by hand, just to make sure that everything is free. The carriage is started first, then the spinners are started, and the machine is run for 3 minutes. Now the loading wire has served its purpose and can be removed and discarded. The flame of an alcohol lamp is used to break the wire before pulling the end through the load. The idea is to taper the wire end so it cannot damage the whole surface. Next comes the step wire. Not only is the end burned off, it is further smoothed and straightened with very fine emery cloth before starting to thread it through the jewel string. Running the spinners makes it easier to coax the thin wire into the load and out the other end. Now the step wire is brought into its starting position, the same as for rough opening. The wire is pulled through the load, until the step which won't enter the jewel stops it, then backed off until that step is out of the way and secured. Before running any step in final opening, the wire must be waved at both ends The carriage and spinners must be worked by hand to ensure freedom. And diamond must be applied before starting the machine, except on the final step. The machine is run for only 1 minute on each step, so as to run no risk of opening the holes more than the next step requires. When the last step is reached, great caution must be used to get the holes up to size, but not beyond. The machine is run for only a few seconds on the largest step, then the whole wire is removed from the load so that a test jewel can be taken out and gauged for hole size. A hot knife point will pry a single jewel out of the string without disturbing the rest of the load. Then the jewel must be washed with a little solvent so it can be gauged. At this time, the hole should still be a little undersized so that the additional running time needed to bring it exactly to size can be estimated accurately. This time will be only a matter of seconds and should always be carefully figured so as not to run the holes too large. When the test jewel finally gauges just right, a takeout wire is threaded through the load to hold the finished jewel. Then the spinner is turned upside down, a tray is put under it, and the wax is broken away with a special tool. If this is done with care, the takeout wire will not be broken. This leaves the string of jewels free so they can be lifted out, and the ends of the takeout wire tied together to hold the finished batch for delivery to the cleaning department. Most of the dirty oil and wax left on the jewels by the hole opening operation is removed by cooking them in a caustic stripper bath. Then, after rinsing and drying, the jewels are acidized. The first step is to cover them with nitric acid. Then a similar amount of sulfuric acid is added to the nitric. Then the test tube holding jewels and acid is put in a beaker of hot oil. The boiling acid removes the last trace of foreign matter and chips, leaving the jewels looking like this, thoroughly clean and ready for further processing. Another method of cleaning is by pumping, mainly done to ensure that all stray diamond particles are removed from the holes. Jewels to be pumped are loaded into small brass cartridges which have a fine mesh screen at the lower end. The tight-fitting covers also are made with screens, so that when the cartridge is closed, it forms a tube with each end closed by a screen, the jewels being in the middle. These cartridges are held in a rack or frame which holds two layers of them arranged so that pairs of cartridges are end to end, forming continuous tubes. The assembled rack is put into a brass barrel which fits on the bottom of the pump. Then a large can containing cleaning fluid is placed so the open lower end of the barrel dips into the fluid. The pump sucks the fluid from the can up through the cartridges of jewels, and on each return stroke forces the fluid down through them and back into the can. After this has gone on long enough to clean the jewels, the pump is stopped, the cleaning fluid taken away, and the barrel removed. The cartridges are taken out of the rack, and finally the jewels are emptied into mesh baskets, in which they will be rinsed and dried. After the hole opening operations and the subsequent cleaning, all holes must be gauged. This is done by inserting a slightly tapered chromium-plated steel needle into the hole. The larger the hole, the further the needle will protrude. The marks on the card are so placed that when the hole size is within specified limits, the end of the needle will come between the two lines. Jewels are usually counted by weighing them on a special balance built for the purpose. The first step is to weigh a counted sample from the lot. The weight of the sample is then set up on the slide rule. Then the remainder of the jewels to be counted go into the scoop with the sample and onto the pan of the balance. The total weight is indicated on a special illuminated scale. The slide rule quickly translates total weight to total number of jewels, and that's all there is to it. This type of counting is done after practically all major jewel operations. This girl is about to load a batch of jewels for finish or concentric grinding. Dipping first into some grease, then into the jewels, she comes up with a dozen or so of them stuck to the end of her finger. With the aid of a large magnifying glass, she now proceeds to string up the jewels by spearing them one at a time with the pointed end of a nylon gut or steel wire. When she gets about enough strung up, she checks the load by measuring it against two marks placed the proper distance apart on the bench. Now the string of jewels must be clamped in the bow, which will hold them in the grinder. First, the bow is fastened in the vise, then one end of the string is clamped tight to one end of the bow. The other end passes through the clamp at the other end of the bow and is made fast to the tension arm there. On jewels with very large holes, a little extra tension is put on the string while the remaining clamp is tightened. Then the jewels are tested for freedom and the load is ready for the grinder. For finish grinding, the loaded bow of jewels is held in a movable carriage in the grinder. One important feature of this grinder is that the jewels spin freely on the string while being ground. This assures the outside diameter being concentric with the hole. The bushings, or slender tubes loaded at each end of the bow, enable the end jewels to pass all the way across the face of the lap, thus securing uniform grinding. The distance between the lap and the rubber roller determines the finish diameter. As the bow reciprocates, it is at the same time lowered slowly until the jewels are exactly on the center line of the lap and the roller. Then the machine stops, and the operator can remove the jewels for gauging and possible regrinding to get them down to size. Since this is the last time the outside diameter of the jewels is touched, it is a logical point for gauging the diameter. This is a standard dial gauge mounted on a special stand designed for motion economy. The jewels that gauge OK are pushed into the central slot and drop into the cup below. If any are undersized, they go into the hole at the right. The oversized ones go to the left. On this dial, each division is 1/4 of a hundredth of a millimeter. On good work, there should be no more than one reject out of 100 jewels. The next major operation is cupping. It is done on a broaching machine. The machine has 4 identical heads, which the operator can keep going at once. This machine is versatile. With the aid of various shaped tool points, it can be set up to perform any one of several types of operations, of which cupping is only one. Here is a greatly enlarged model of a jewel to help show how cupping is done. The jewel is held in the chuck, which rotates it clockwise. The tool is made of borax and diamond powder. It has a rounded point and spins counterclockwise. It cuts and polishes at the same time. Here's the broaching machine again, and as the tool completes a cut, the operator lifts it clear. A vacuum line plucks out the cup jewel, and the operator sets in a fresh one with tweezers. The cutting oil used on this job is a mixture of lard oil and kerosene. In only a few moments, the cup is formed. Then the tool lifts, the chuck stops, and the vacuum pipe swings into place once more to take the jewel. So the cycle continues, the operator loading the chucks as fast as the cups are finished. Behind each of the 4 heads is a little lamp, which lights to indicate the completion of the cup in that head. Each pivoted arbor that holds a spindle is weighted to put just the right pressure on its tool point. A pointer indicates the progress of the cut. When it is deep enough, a contact lights the lamp and an adjustable stop halts the tool point. And so the cycle goes. The jewel goes into the chuck spins at 3,300 RPM, the tool goes the other way at 19,000, and almost before you know it, another jewel is cupped. This model shows the shape of the jewel at this point. The hole is still straight and must now be given an olive shape. This is an olived hole. It presents a smaller bearing surface, produces less friction, and makes for better lubrication. Oliving is done by drawing a diamond-coated nickel-silver wire back and forth through the hole of the rapidly spinning jewel with a sawing motion. On the actual oliving machine, the jewel sits between 2 spinning hard rubber wheels. The jewel is thus driven at a terrific speed, often over 100,000 RPM. The wire is held in a steel bowl. The small amount of diamond powder needed for each jewel is applied by touching the wire to a diamond-saturated felt pad as each jewel is started. Only experience can teach an operator how many and what kind of strokes are needed to produce a perfect olive shape in a hole and bring it exactly to size. The next operation is to convex the jewel. This, by cupping, is done on the broaching machine. The tool point, or broach, has a concave end, corresponding to the shape of the convex surface required. The secret of success on this job is to have a very dense, non-porous brooch and to get the end of it to the proper concave shape. Here is how brooches are prepared. An oxyacetylene torch is set up so that it can be used to heat a heavy alloy cast iron plate, which is located at an opening in the top of the bench. The gas is regulated so that the plate shows a dull red spot over the flame. Then a mixture of borax and diamond powder is put on the hot plate, using sufficient powder to make several small brooches or one large one. Now, using a flat steel tool, the operator begins to work the powder. The heat, melting the borax, will reduce the mixture to a slightly sticky dough. The object of the manipulation is to keep the powder in motion, so it will heat and soften uniformly, meanwhile gradually rolling it into a cylindrical shape. The consistency of the mixture can be controlled by working it on or off the hot spot on the plate. The rolling process gradually works the borax and diamond mixture into a hard, uniform, dense mass. It is continued until the required size is reached. When finished and cooled, this is how the brooches look. A special diamond tool is mounted in the broaching machine chuck. When the brooch is run against this tool, the diamond will gradually chew out the flat end of the brooch, leaving it hollow. But the surface is still too rough to do a good job of convexing. So it is run in by taking a light surface cut on a run of jewels. At first, the jewels will show a poor finish on the convex, but as the brooch wears smooth, the finish will improve and finally become acceptable. Then the broaching spindle is readjusted to make a finish cut. The same jewels that were used to run in the brooch are put through again. Thus a new brooch can be broken in without spoiling any jewels. Chamfering the corners of a jewel is also done on the broaching machine. The end of the brooch used is flat, and the spindle is set at the angle of the chamfer. Brooches are usually designed to produce a high polish as they cut, such as for cupping and convexing. But for chamfering, the brooch is made of coarser diamond and produces a rough finish. Now the flat surface of the cup side of the jewel must be polished. The jewels are blocked just as for the surface grinder, except that the center of the block is not used. They first get a dose of diamond paste, then are fastened to the floating arbor of the machine and pressed against the spinning lap. Oil is used on the lap to keep the friction down. Even so, the jewels being polished heat up very rapidly and must frequently be laid aside on this cooling plate, which is hollow and is kept chilled by running water. The mechanic keeps two blocks going at once, polishing one while the other is cooling off for another run. The lap used on this job is a disc of boxwood. It is hard, close-grained, and smooth, and is capable of producing a very high finish. Sometimes, on heavy polishing like this, it helps to add a little extra diamond to the lap from time to time. Now the first block has cooled off enough for another run. The trueness of the lap and the uniformity of the diamond powder are all important in this operation. At the first sign of scratching of the jewel surfaces, the lap must be refaced. From time to time, the thickness of the jewels is checked on a gauge, making sure, of course, that the block is cool when it is gauged. When the quantity of jewels is small, flat polishing may be done on the tripod polisher. Each of the three armed spiders holds 3 of the small blocks of jewels, and presses them against the surface of the boxwood polishing lap. The operator gives the spindle a turn by hand before starting the motor. Oil and benzene on the lap keep the jewels from overheating. After a short run, she stops the machine, takes out one of the spiders, removes a block of jewels, and checks it with a gauge. This is repeated for all the other blocks to make certain that all the jewels are being polished down uniformly. These apparently are still too thick, so back on the spider they go. Now for a little diamond on the jewels, then back into the polisher for another run. Oil is applied to the spider pivots, oil and benzene to the lap. This cycle is repeated until the required thickness is reached. Jewels are gauged for thickness after flat polishing, as well as at other points in their manufacture. This gauge stand is provided with a sapphire insert in the table where the wear is most severe. Disposition chutes make it easy to handle the work rapidly. Oversized or undersized jewels go into the side chutes. The OK jewels go down the front chute. This is a brushing machine. It is used to put the final polish on the convex side of the jewels, and at the same time, round the outside corner slightly. When blocking jewels for brushing, considerable space is left between them to allow room for the bristles of the brush to act on their edges. Diamond paste is applied to each of the blocks in turn. Then the machine is started and the brush swung into position. An interesting thing about this machine is that it can be set up for a large variety of brushing operations, such as getting a rounded chamfer on an outside edge or a rounded countersink on a hole. The speed of the brush, the speed of the arm, the pressure of the brush, and the coarseness of the bristles all have a pronounced effect and allow a number of types of work to be done. This is a setup for countersinking holes. There are two reasons for countersinking. On some jewels, it provides clearance for pivots with a fillet at the shoulder. On almost all jewels, it is done to give the edge of the hole a smooth, chip-free finish. The tool looks like a small pencil, but in this pencil, the lead is a borax and diamond brooch. The operator touches the point of the brooch to a little felt pad soaked with oil before countersinking each jewel. The jewel is supported and driven by a spinning rubber cushion. As the operator finishes each jewel, she flicks it off the cushion with her tweezers as she puts the fresh one in place. From time to time, the point of the brooch must be sharpened. This each operator does for herself, using a small, hard, white stone for the purpose, twirling the tool rapidly to get the point round and smooth. As the jewels are finished, they drop into a ring-shaped cup, which surrounds the rubber cushion. This is how the cup is removed and emptied when a lot of jewels is completed. With the countersinking of the hole, work on the jewel is completed. Now is the time to make certain that it meets every specification. Once more, the hole is gauged. Once more, the thickness is checked. And once more, the diameter is measured. Then it goes under the microscope for a searching inspection that will reveal any surface defect or flaw that might affect its usefulness. Some flaws affect neither the looks nor the performance of a jewel. A set of large-scale models is kept on hand, carved and painted, to indicate which kind of flaws are permissible and which are not for each particular type of jewel. The green marks indicate defects which may be passed. The red ones are the no-go flaws, and anything resembling them is cause for rejection of a jewel. This is the final inspection and is the only time that the jewel is thoroughly examined all over. One at a time, each jewel is picked up, scrutinized, turned over, and scrutinized again. These being chronometer jewels, they are shipped in a special case to avoid possible scratching. Those that pass this final inspection are fully fit for the job they have to do, ready to take their places in the finest timepieces man can build. Timepieces whose function is so vital that sometimes the destiny of battle fleets has depended absolutely upon their accuracy, and through them, the course of great nations has been affected. And that's the kind of a thing a jewel bearing is, a sort of a concentrated element of accuracy, whose size is no clue at all to the profound influence it has on the affairs of men.